This lesson introduces exponential functions. Exponential functions have the form y is equal to a to the power x, where a is the base and x is the power, or sometimes that will be called the index or the exponent. Examples of exponential functions would be y is equal to 3 to the x, y is equal to 4 to the x, or even y is equal to 2 to the power 3x plus 5. So the power can actually be an expression in itself, an algebraic expression. Now what we'll do on the next slide is we'll have a look at the graphs of these functions. They all have a similar shape, and depending on the base, they change and alter slightly from each other. So graphs of exponential functions all have the same shape. So you can plot a graph of any function. It doesn't need to be exponential, but you can plot the graph of any function by creating a table of x and y values. So that's what we're going to do for the function y is equal to 2 to the x here, to give you an idea. So we'd pick x values, and then we'll have corresponding y values. I'll just draw a wee table. So we'll take the values for x, -4, -3, -2, -1, 0, 1, 2, 3 and 4. And then using our calculators we could work out what these values were. So you would do 2 to the power -4 and you'd get 1/16. 2 to the power -3, 1/8. So these are fractions, or you could write them as decimals. I'll just carry on filling this out. So 2 to the power 0 is 1. That is one of your indices rules that hopefully you remember from previous study. 2 to the power 1 is just going to be 2. And then we've got 2 squared, 2 cubed, and 2 to the power 4. So that gives us coordinates that we can use. So our coordinates for a graph would be -4 over 1/16, -3, 1/8, -2, 1/4, and so on. So you'd keep going with all those values. And on the next graph I will draw, it will be a sketch, because obviously I don't have any graph paper here, but I will draw a sketch of what this graph would look like. So we'll have our coordinate plane, and the basic shape of an exponential function would be something like that. It should be curved. My pen is obviously going a bit wonky in the middle there. This point here would be 1, and then you would just have your values going along here. Now the point of an exponential function is it starts to increase dramatically. Because we're looking at powers here, you can see on the right hand side of the graph that it increases very sharply as x gets bigger, y is getting exponentially bigger basically, so much bigger. But on the left hand side, when x is negative, the graph gets smaller and smaller, and at this point here it's getting closer and closer to 0. It never actually equals 0, but it's getting closer and closer to 0. Now before I go on and write out some of the key points of this graph, what I'm going to do is I'm just going to show you some other functions on the same graph to show you how they would alter. So I'll change the colour. So let me first of all write in that's y is equal to 2 to the x. We'll go for y is equal to 3 to the power x. Oops, not quite fitting in there. And the final one I'll put in y is equal to 4 to the x. There we go. So as the base increases, the graph gets steeper. As the base gets bigger, and as we said, I'll just put this in here, as x tends to, well, say negative infinity first of all, so that's where this arrow was here. So as x tends to negative infinity, the function tends to 0. So it's getting closer and closer to 0, and as x tends to positive infinity, which would be up at this point here and here, so the x values are getting bigger. The graph for the y, fx, is also getting bigger, so it's going towards positive infinity. Just remember that that arrow here and here means tends to or approaches. Right, on the next slide we will talk about the key points. So the key points on the graph were 0, 1. So all exponential functions go through the point 0, 1. And this is because, if we just do the math, so since y is equal to a to the power 0 is equal to 1. So any base, it doesn't matter what the base is, a, if we raise that to the power of 0, we get 1. So that gives us our coordinate 0, 1, x 0, y 1. And the other key point is 1a. And again, this is because since y is equal to a to the power 1 is equal to a. So anything to the power of 1 is just the number itself. So we've got x equal to 1, y equal to a. So they are the two key points. And by a, that would be the base. So that would be whatever number here is. That a will be different depending on the function. The other important thing about the graph is the graph is always positive. And by that we mean the y values are always greater than 0. So there's nothing below the x-axis, all the y values are positive. We use exponential graphs in science and maths a lot, engineering, and for example they're there to represent things that are increasing rapidly. So for biology that may be something like bacterial growth. So every time a bacteria cell divides, it splits into 2. So the next time they divide, you've got 2 splitting into another 2, so the number increases exponentially and goes up very sharply. The graph increases sharply. Okay, what we're going to do now is we're going to have a look at the graph when we have a negative power. How does that affect the graph? Okay, so the graph of y is equal to a to the minus x. Well, we learned in outcome 1 of Maths for Engineering 1 that when we transform graphs, we can move the graphs around the coordinate plane. And in this case, what we've done is we've changed the power of x, so that will be a reflection, and the graph reflects across the y-axis. So if we redraw, so our normal exponential function, we'll say, looks like this. So that was the one on 2 slides ago. Then the function for the negative power would look like this. Y is equal to a to the power negative x. So it's a reflection across the y-axis there. Basically what's happened is all the x values change sign. So it's a reflection across the y-axis. So what are our key points on this graph? So our key points, well, hopefully you noticed we've still got the 0, 1, but this time we have 1 and then 1 over a, or you could think about that as 1a to the minus 1 if we were using our indices rules. Remember that when we have something which is the reciprocal, 1 over a, we can also write it as a to the power minus 1. But again, you will have noticed that the graph is always positive again. So y greater than 0. There, no part of the graph is below the x-axis. Right, there is one other exponential function that we're going to look at, and this is actually called the exponential function. Okay, so the exponential function is y is equal to e to the x. So the base here is something called e, and e is an irrational number. It has a value of approximately 2.718. And again, this is often used when we are talking about exponential functions in science and engineering. To get this on the calculator, you would press your shift button, followed by the ln button. So ln is the natural log, which we'll be talking about later on. But you would press that button and you would get an E appearing on your calculator, and then you would be able to input a power. We write the exponential function as either y is equal to e to the x or y is equal to exp x. So instead of writing the e for the base, you can write exp, which again stands for exponential. Right, we'll have a look at the graph again, but hopefully you can imagine it's going to have the same shape as the other graphs that we've looked at, but we'll do a quick table of points and have a look at the graph here. Okay, I've produced a table of points for the function y is equal to e to the x, and hopefully you can see from 1, power 1, 2, 3, 4, you can see that it sharply starts to increase. It goes from 2 to 7 up to 20 to 54. So that's the effect of the exponential function there. And if we draw this, okay, y is equal to e to the x. So again, our key points, we have 0, 1, just like all the other exponential functions. And again, this is because we have y is equal to e to the 0, anything to the power of 0 is 1. And the other key point this time would be 1e, because our base is e. And this is because y is equal to e to the power 1 is e. And finally, you should again notice that the function is always positive. So the graph is always positive. So y is greater than 0. So the same as the exponential functions we would looked at before. Now what we need to be able to do with this graph and these functions is to be able to look at the graphs of the functions and to be able to identify the functions from them. So we'll be given pictures of graphs, data about those graphs, and we have to work out what the function is. So I'm going to do a couple of worked examples here for that. So identifying graphs of exponential functions. Right, so example 1, we have to find the value of a in the function y is equal to a to the x that passes through the point 225, and then write the equation of the exponential function. So what we're trying to find there is the base in this example. So we've been given our basic function y is equal to a to the x, and we've been given a point 225. So we'll do the working on the next slide. Okay, this coordinate, the 2 is the x value and the y is the 25. So what we can do is we can take these values of x and y and substitute them into that formula. So 25 is equal to a to the power 2. So what's that basically saying? That a squared is equal to 25. So to solve for a, we take the square root of 25. And we're left with 5. So our equation is y is equal to 5 to the power x. So in this case, our base was 5. Okay, so in example 2, we are asked to find the value of a again, but this time when we look at our function that we've been given, a is not the base, we have the exponential base here. So a is something that's multiplying the exponential. And that graph passes through the point 0, minus 4. And again, we're asked to write down the equation at the end. Now, just before I go on to the next slide to solve this, I just want us to have a look at this graph. All of the values have now become negative. All of the y values have been negative. This graph has been reflected over the x-axis. So that would suggest that a is going to be a negative value, that we're multiplying by a negative value to give us this graph that is upside down. Okay, so we'll start with writing the function. A times e to the x, and we have the point 0, minus 4. So again, 0 is our x, and y is our minus 4. So we sub in. So we have minus 4 is equal to a times e to the 0, and over at the side we'll just say, remember that anything to the power of 0 is 1, so e to the 0 is going to be 1. So we're going to have minus 4 is equal to a times 1, so a is just minus 4. And that is what we expected. We expected a to be a negative value, so we have the function y is equal to minus 4 e to the x, and it is that negative sign in front of the 4 that has reflected all the values over the x-axis to give us a function that basically looks like it's upside down. It's the mirror image of the function 4 times e to the x, and I'll just draw that for you. So there's the function that we had, y is equal to negative 4 e to the x, and then what we could do is we could put in y is equal to 4 e to the x, and hopefully you can see that they are the mirror image. I can't get my x to work, there we go. They are the mirror image of each other, and it's just the negative sign that is different, which has caused that reflection. Right, let's look at one final example. Example 3, we're asked to find the value of a again, but this time our function is y is equal to a times 10 to the x, so our base is 10 in this case, when it passes through the point 1, 5, and again write the equation of the exponential function. So our function was y is equal to a times 10 to the x, and our value was 1, 5. So x is 1, y is 5, 5 is equal to a times 10 to the 1. Now, 10 to the 1 will just be 10. Anything raised to the power of 1 is just the number itself. So we have 10a is equal to 5. So a will be equal to 5 divided by 10, which is a half. So a is equal to a half. So we have y is equal to a half times 10 to the x, or we could write y is equal to a half 10x. That seems a bit odd to be multiplying what looks like two numbers together, but it's not. The half is a number, the 10 is the base of the power, so it's not a case of writing that as 10 divided by 2. Can't do that there, you've got to keep the half separate. And that concludes this video.